Hey, so yeah, I'm Tom, and today I'm going to try to talk about some of the work I've done in Java to try and make a programmer-friendly crash consistency model, and also to just talk about some lessons I've learned throughout the way, and maybe what some unsolved problems still are. As you all know, there's a lot of promise to NVM. By using it, it's a good combination of performance, capacity, and persistency. In theory, if you want it exposed at the application level, you would no longer have to serialize data out to secondary storage for durability. And two, it's also byte-addressable, so it ties naturally to a load store interface. However, though, if you actually want to use NVM correctly in application, it's just not that simple. Because there's still volatile processor caches, you have to take that into consideration and make sure you insert all the necessary cache line writebacks and fences to make sure stuff's actually in a persistent memory when you want it to be. Likewise, too, in reality, you're probably going to have a collection of writes that you want to either all commit or none of them to commit at all. So there needs to be some type of software support for failure atomicity, and you have to do some type of logging or epochs or something in that regard. So really to make it at least somewhat possible for application to make persistent applications, frameworks need to be used. So as I kind of what I'll first do in this talk today is I'll kind of talk about what some of the drawbacks I feel are for current NVM frameworks, especially for like managed languages such as Java or Scala and such. Then I'll kind of give a quick sales pitch of what my, well, I guess maybe not that quick, but some information about what my work is and what I've been trying to do in my research. Then I'll try to then describe some of the lessons I've learned throughout my research. I guess the quick summary would be that there needs to be language level support. And then finally, talk about some of the unsolved things and kind of decisions that still need to be made. So right now, if you want to, at the application level, once again, this is the application doing cache line writebacks or fences. This isn't like some type of file level abstraction. This is directly in the application. If you want to make it crash consistent data structures, you really kind of have three options. You can manually insert all the assembly instructions and system calls you want, which is too hard. Some frameworks expose persistent memory as a buffer, and then you can interact with that buffer directly and try to make things, use that in a correct manner. Or right now, you can use a library framework, but really I guess there's two out there. There's NVM Direct and PMDK. But PMDK probably has the most push behind it right now. The alpha are C, C++, Java, JavaScript, and maybe Ruby bindings too. And within PMDK, there is support for failure atomic regions, and they do have some libraries for persistent data structures already. So given the simple code here, where you just have a linked list, and you have a simple method where you just add in an element to the front of the list, if you actually want to do this in C right now, and using PMDK, the code will look something like this. And this may or may not be correct. I didn't actually validate it. But it requires a lot of extra red, as you could see, because you have to declare what the struct's supposed to be. You have to use these wrapper calls to make sure you have pointers that are independent of where the actual address spaces are, and provide some type safety. You have to add transactions. You have to change the way the news are working. You have to declare your intent of what needs to be logged. So it's pretty complicated to write C code in PMDK currently. The other main options, you could use the C++ bindings instead. This looks a lot simpler than what was before. Now within the struct, you do still have to explicitly identify what fields need to be persistent. You have to do some things about transactions. You have to use different allocation commands, but somewhat more reasonable. The trade-off, though, is actually the C++ bindings perform a lot worse than the C ones. Because it's doing stuff at a per field level, it affects how they're making the logs, and they have to log at a per field level, as opposed to logging the whole object preemptively. But as I said, my goal is to kind of make something that's more programmable, and programmers like to use higher level languages and like to use the abstractions that they provide. So when you start to think about those types of languages like Java, C#, Scala, etc., in my opinion, these current frameworks really aren't a good match for it, and really for two reasons. The first one is, and this is really important, I think, for languages like Java, is that you can't use existing built-in libraries and data structures. because these existing libraries don't contain the necessary persistent markings. In some languages that has a lot of baggage in the past, there's already kind of maybe been a splitting of what types of data structures you use. So trying to learn some other one and using some other library maybe could be acceptable. But in something like Java, there are just so many built-ins provided, and they're the de facto things always used. So if you have to now all of a sudden switch to using different data structures, that's going to be really problematic. And the second thing is more of a conceptual, is the fact that in these current frameworks, you really kind of have, it requires the programmer to make a lot of just other considerations. They have to think about what persistent memory is, when it needs to be pushed back to it. Whereas they're used to different levels and higher levels of abstraction. Well, they just want a new object, and they don't really care where it's allocated in such a way, right? So my solution to these existing shortcomings was to design a new NVM framework. And for this framework, I've really tried to focus on programmability first, and then rely on compiler optimizations later to achieve high performance. I've also tried to design it in such a way that the framework's tailored to managed languages, and it's able to effectively leverage the managed language runtime features. So this new framework I made, I called AutoPersist. The name is because the framework could automatically do a lot of the work needed for creating a persistent application. So not exactly a clever name, but AutoPersist right now is currently targeting Java, but we implemented it within the Maxine JVM, I guess. So it's a research JVM that allows for a fast prototyping of features. But because for AutoPersist, really what we're doing is we're adding a couple annotations to the Java language, but most of the work is done at the JVM level, affecting extending the semantics of the JVM bytecodes. But because of that, it could be easily extended to other JVM-based languages. You just need to make sure you have the proper annotations in that, but it should work okay. So when designing the programming model for AutoPersist, I kind of had three goals in mind. The first one is I wanted to make sure that the programmers didn't have to add a lot of markings to their code, because the more markings they have to add, the more potentials they have to make mistakes and mess up things. The second is I thought it was really important to make sure that existing libraries could be used. They didn't have to learn a whole new set of libraries. And finally, I wanted to make sure that failure atomic support was provided and also need only minimal markings. So as I said before, the reality is that for any substantial applications, there's going to be a large set of stores that have to appear to complete atomically from a persistency perspective. So what we've come up with is really the users in AutoPersist have to identify kind of two sets of markings. They have to identify what a durable root set and what the failure atomic regions should be, just kind of demarcate the begins and ends of these failure atomic regions. So what I'm referring to the durable root set is this, what the durable root set is the set of objects directly referred to at recovery time. And for these, they just annotate them with a durable root. I'll give examples of really what should be labeled as a durable root in a couple slides. And then failure atomic regions are kind of just what the name implies. It's stuff that has to either all complete or none of it complete at all. So given these markings, the durable root set and the failure atomic region markings, the AutoPersist JVM runtime then dynamically detects and monitors the transitive closure of these durable roots. And it does all this dynamic detection or monitoring to make sure that everything reachable from a durable root is an NVM, and to make sure that everything's reachable as an NVM, that requires it to dynamically move objects through NVM throughout execution as they become reachable from the durable root. The other thing AutoPersist does is once an object's in NVM, you also need to make sure that stores to it are done in a crash consistent manner. So it automatically inserts the needed logging, cache line writebacks, and fences to make sure they complete in an intuitive order. And I'll describe its persistency model also in a couple slides, but it's a combination of epoch for failure atomic regions and sequential elsewhere. So really, what should be a durable root? Let's say you just want to make a simple data structure persistent that's just an array of ints. Well, that's self-contained, so it's pretty obvious. You just make that, you make sure you label a pointer to this data structure as a durable root, and you're good to go. It gets a little more complicated, though, if you actually have an array of objects. Because what an array of objects is just an array of pointers to other objects. So if you're just to make that array of object pointers persistent and nothing else, that wouldn't be good enough. Because in reality, then, if you were to crash here, all these objects wouldn't be recoverable, so you just have a bunch of dangling pointers and nothing else. But because AutoPersist, we're trying to monitor the transitive closure, it will detect and make sure that all these objects reachable from this initial array of pointers is also persistent as well. So really, because of using this reachability property, I found that you don't have to add that many markings to make data structures persistent. So like to describe a simple example, if you have a tree, all you need to do is make the root of the tree persistent, or label that with the durable root. Because everything has to be reachable from it, it will also be persistent as well. Likewise, for like something like a linked list, you just need to make the head node point to a durable root, and then once again, because everything will be reachable, it will be persistent as well. So I think, at least in my opinion, I think it's a pretty simple way to identify what needs to be in persistent memory. So kind of looking back at the same code example I did before for the C and C++ bindings of PMDK, in AutoPersist, all you need to do is label the head as a durable root and everything. Yeah, sure.
So that's an extension to the parser or something? Or is that
so this is just the annotations in Java. So you could specify annotations to be actually kept in the code all the way to the JVM. So you could read it when you're actually generating the code.
You can add essentially language extensions by doing it.
Yeah, you can make stuff be interpreted differently than what it would be originally intended for. But so yeah, in this example, you just have to do a durable root. This is kind of cheating because it's a very simple code, so I don't need a transaction here. Because I'm doing sequential persistency, so these things will complete in order. And the fact that it's garbage collection, I don't have to. Whereas in like a language like C or C++, even for something simple like this, you need a transaction to make sure the memory allocation would be done in a correct manner. But as I said, we do have support for failure atomic regions as well. So the big tricky thing with AutoPersist is dynamically monitoring what this transitive closure is and making sure everything is moved to NVM as necessary. Because let's say you have this array or this graph of objects where each of the circles is some object and some arrow is another object it's pointing to. And let's say you now want to have G point to E as well. And there's a volatile and a non-volatile heap. If you just let that G point to E without taking any preventative actions, this would be wrong. Because now you have a pointer from NVM to volatile memory. So if it were to crash, this is meaningless. So what happens in AutoPersist instead is that before this actually G could point to E, E has to be moved to NVM, but also because C is pointed to by E, C has to be moved to NVM as well. So all this movement's done first, and then the pointer is updated. And just due to time limitations, I don't really have time in this talk to how it gets kind of complicated to do it, because potentially other threads could be, in a multi-thread environment, one thread could be having to move objects while other threads may be mutating the object space as well. And making sure this is done in a correct way requires kind of some careful consideration. But it's also a lot like concurrent garbage collection too. So it's problems that have been solved before as well. So as I kind of said before with regards to its persistency model, we have both epoch and sequential persistency. Within the failure atomic region, since nothing's going to be visible until the very end of it, nothing actually, you can complete all those cache line writebacks out of order, provided that it's aligned with the login write, because it just needs to complete by the end of it. But outside of these failure atomic regions, we're using sequential persistency because it's really the easiest one to understand. You know when stuff's going to complete, because it's you can just draw a line in the code. Some stuff has happened and maybe some, yeah.
Well, I've been through this, trying to figure this out, the sequential one. It seems to me, maybe maybe you've already dealt with this, but if you are at point A in the code, now you do a memory copy to a store, and then you do a CLWB. What happens between the store and the CLWB, the system crashes? Do you know whether the store got done or not? That's what I've been trying to figure out.
No, you don't know, but it's either that happened or so what the point of consistency or persistency would be, this would be the previous store, right? But before that store can even start to execute, the previous store is completed in a persistent manner.
But you don't know whether that one is actually completed because, if you get, I just want to make sure I understand this. I realize it's not very likely, but it still could happen. because I was trying to figure out, say, well, you can't, if you say, okay, it was done before, everything's done before you get there, but between the store and the CLWB, you don't know whether that store has been put on the is actually persistent or not. It's just for that brief interval between those two. It could be inconsistent. Is that my wrong? Or is that...
No, that's true, and that's actually, so I have some slides on that later. So if you want like synchronization primitives, this kind of separation of visibility and persistency is a big problem. And that's something that's kind of one of the big unsolved problems yet, that there are some there are not hardware, there are some software solutions right now, but what hardware solutions actually come out remain to be seen, and when they've come out remains to be seen. But yeah, no, that's a big problem for trying to, in a multi-threaded environment, what type of data structures. Well, sure, yeah.
1 and 2, in between 1 and 2, we don't know. Okay, I just want to make sure I understood.
Yeah. But yeah, so as I said, in this model, we're having to do a lot of guarded actions and kind of check to see, do some extra actions in some situations. So we have to, for instance, check to see if you're storing to a durable root, an object reachable from a durable root, if you're in a ferroatomic region and you have to do some type of logging. So to kind of do all these different actions within our runtime, what we have to do is we have to add an extra object header word to each Java object to contain some persistent state and also a forwarding pointer in case we've moved an object from, so yeah, one thing I won't really talk about much here, but if you move an object from volatile to non-volatile memory, you don't want to have to update all the pointers to that original object when the object's moved. You just want to make sure that all pointers within the non-volatile memory are correct. But all pointers within the volatile memory could still have a level of indirection because all those pointers, if you were to crash, go away anyway. So you could leverage the original object then to act as a forwarding object to the current location for all the objects in volatile memory. So that's kind of, for like one instance of using this extra header word. We also could use it to collect profiling information that we could use to optimize the code later on. Another thing we have to do is really to make this work, as I said, for not only Java, but for all languages or all JVM-based languages, is that we extend the semantics of several JVM bytecodes to perform all these checks for forwarding objects and to do these extra actions on stores to make sure that they do the cache line wrapbacks and fences. So all the field accesses, both for storing and loading, all the array different bytecodes, and then the monitor ones as well for like locks, I think were the main ones that we had to add extra behavior to. The way we're adding extra behavior to, if you're just running a regular volatile non-crash consistent program, the semantics will be exactly the same because none of these extra actions will be activated. It's just a matter of once you have these annotations within the code, then it'll start to do extra things. So because we have to do all these extra actions, it really becomes problematic if you're just, say, running a normal application and you don't care about persistency, you don't have NVM, and you don't want to, obviously you could just run a different version that doesn't do any of them, but say you're in a hybrid system where some objects should be in an NVM, some objects should be volatile memory, you don't want to have the overhead of checking for all these things all the time. So one optimization we do, because JVM JIT traditionally are multiple tiers, it allows us to collect profiling information in one version of the generated code, and then regenerate code to make sure that the common paths, the expected behavior is on the fast path. So we're able to do that to limit this check overhead when it's not needed. Another trick we're able to do is we don't want to have to be copying objects all the time from volatile to non-volatile memory, especially as non-volatile memory becomes faster and you want to you could hopefully use it all the time. But so what we're able to do is we predict which objects will likely be moved to non-volatile memory in a future point, and we could just pre-allocate those objects in NVM. So I guess I'm running a little slow, so I might speed through this kind of fast. But we did, as I said before, implement this on Maxine. We were given early access to a Cascade Lake machine that had opt-in DC memory. And what we did is we compared against Espresso. And Espresso is just another kind of Java-flavored NVM framework that came out a year and a half, or I guess, yeah, just a little more than a year ago. In this one, you have to actually explicitly allocate, say which objects need to be allocated at NVM, allocation time, and insert all the cache line writebacks and fences you want. So for demo applications, we modified the backend of a key value store server to have two different data structures that were persistent. We did a B+ tree implementation and a functional hash map implementation. And we evaluated this key value store server running the YCSV workloads. The other set of applications we did was we did some simple data structures, just different combinations of array list and linked list implementations. And to evaluate their performance, we ran on each of them a different random sequence of get, set, update, and delete operations. Yeah.
Have you published the results of the performance, the first thing at the top of the TV store?
I've published normalized results relative to other things, but in terms of, yeah, there's still overhead right now. I mean, the big thing for this framework right now, it's a proof of concept in Maxine, right? Maxine's not hotspot. So the performance numbers will get better. It's better than using pmemkv with the Java bindings. But that has a big J&I overhead, and it also has to copy data all the time. So it's not really an apples to apples comparison, but it's able to outperform that. But before showing those results, just some quick meta information about the number of markings needed. For an AutoPersist, for these key value store things, we only needed 10 markings, whereas for Expresso, we needed 100. For the KV stores. And then for the kernels and AutoPersist, we hardly needed any. Well, on Expresso, you needed a lot, would be the quick summary of that. And then two, I didn't necessarily expect at the beginning, but what actually happened is that AutoPersist outperformed Expresso too, but it really outperformed it for update-heavy workloads. And the reason for this was that the way cache line writebacks have to be done, especially when you have to expose cache line writebacks to the programmer versus being able to do it within the JVM. So because from a programmer for Java, they don't really know how the layout of the object's going to be. So they have to be super conservative if they have to implement cache line writebacks themselves, because they don't know what the cache line alignment is. So for each field, you're going to have to do a cache line writeback. However, for AutoPersist, you do know what the layout is, because it's actually implemented inside the JVM. So especially when I'm during the normal execution right now, I'm doing sequential persistency. So all those updates, it doesn't matter what the alignment is. I could do optimization on that plane for the total store ordering. I'm not right now. But when actually moving an object to NVM or making the object initially persistent, in that situation, when it's initially becoming reachable from a durable root, I'm able to limit the number of cache line writebacks to be per a cache line. And that had a huge impact on performance and was able to make it outperform Expresso. The intent of AutoPersist was just making it easy to program. And I expect there's a lot more optimizations that can be done in the future. So on these simple data structures, AutoPersist is even better than, it also, once again, outperforms Expresso, and for the same reason that it's able to have less cache line writebacks than it. But we've had several works on it. I think the main one, if you look at anything, please look at the PLDI one. That gives a lot more information about how we're able to handle this concurrent moving of objects with other threads mutating them, and gives more details about other tricks we do with these forwarding objects and what bytecodes we have to modify and such. And then VE is this optimization we do to limit this check overhead by predicting what the behavior for each of these bytecodes will be, and making sure the code's laid out in such a way that it's optimal for the situation that's likely to be encountered. But I guess that's kind of the sales pitch for AutoPersist. And now let's kind of talk more about what my lessons I feel like I've learned and what problems still exist in general from trying to make a model that's based on reachability, and also when trying to use undo logs. So in my simple experience, I found that identifying persistent objects is hard, and deciding if you have to decide where to put cache line writebacks and fences, it's also really hard. I'm making very simple applications, and I still found myself making a bunch of mistakes. Like, I'm not the best programmer ever, but at least I feel like I'm marginally competent, and it's just really hard to wrap your head around. And once again, these were for very simple applications, to be honest. as you get harder or like, more realistic applications that have pointers everywhere that can reach just weird graphs of different objects being connected, you can't identify all the fields or identify the allocation. It's going to be really tricky. The second thing is, especially right now, the cache line writebacks are super expensive, so you really want to minimize their occurrence. However, if you're using libraries, or even, it's really hard to minimize their occurrence, because what's going to happen right now is cache line writebacks and fences are just kind of generic instructions that you don't know what their intent is. So in a library right now, all they're going to do is have some ASM volatile or maybe some built into some GCC binding. And so they have to insert these cache line writebacks and fences, but they don't know, right now, without any language information, they won't be able to move them around or coalesce them or do anything. They're kind of just at the mercy of where the programmer put them or where the library put them. So right now in PMDK, they're able to kind of get away with it a little bit just because NVM's slow enough that they're able to do a lot for software tricks. They're able to do multiple phases of minimizing the amount of actual cache line writebacks you're doing by combining logs, by recording action, combining redo logs inside DRAM, making sure that you kind of have a log space, and two, also delaying all these cache line writebacks until a phase at the end. And the reality is they get faster and you don't have time and you have better fences in the ISA, you'd want to push some of these up earlier in the code. But you can't really, in the library, you're handcuffed at the moment. So my big takeaway from what I said about programming in these are very tricky is that language support is necessary for multiple reasons. First off, as I kind of alluded to before, is you need to be able to use the existing libraries and APIs that you've used in the past. You can't expect the programmer to use different ones. Even if they're very similar, it just makes porting code or refactoring code to use stuff very complicated. Second thing is, let's say, fine, you save a lot if you could just reuse all these existing data structures, but inevitably you're going to have to make some different types of classes and object layouts yourself. And when you do so, you shouldn't have to declare which fields are persistent or when to persist them. They're just, it's too hard. They'll make a lot of mistakes. And also, the final thing I've kind of been harking on is that you need to have built-in support for failure atomic region. I think that's a given and kind of self-evident, and any meaningful program will use some type of, needs to have notion of rollback. So with regards to in addition to the language support, the compiler also needs to be smart about it. As I said before, right now you could kind of get away with using libraries just because NVM's slow enough. But as NVM gets faster, you won't be able to get away with all these runtime tricks. And if you were to instead, the compiler becomes more aware of what your intention was by inserting all these, well, you don't insert them, the compiler decides where to put them. It could do a lot of smarter things. It could identify where cache line writebacks should be and when they could maybe be moved up, if they could be coalesced and removed. I also think there's a lot of potential in the compiler to reduce the overhead of logging by making sure what type of logging you use, how much of the object you log. Do you just log a field versus do you log are you going to write all the fields of the object and you could initially just write the whole object into the undo log? So I think there's a lot of potential for compilers to do smart things. So as the question he had before, actually no, that's the next slide. So one problem to consider, and this is, yeah, so I guess those were my takeaways, and now moving on to other big problems to address. One of them is that you have to think about multiple threads executing, and multiple threads actually executing with undo logs at the same time. And you have to think about what is and what is not a race, because potentially you could have a correct program from a visibility data race standpoint if you have each thread uses critical sections in the proper way to lock the objects it's going to modify. But let's suppose though, they're very lazy about where they put their failure atomic regions. And they just try to wrap a huge multiple critical sections within the same failure atomic region. The problem can arise that two threads made in their undo logs, these per thread undo logs, each have modified the same value. And you don't know which of those two values, if a crash were to occur, you're supposed to roll back to. So the question, right now, all these frameworks, if they write it in such a way, it's really an incorrect program. because they had to change their locking to make sure the scenario where the undo log of multiple threads wouldn't both have the same object. But to do that, then, so basically a new model has to be proposed where you have to consider about persistency erase-free on top of data erase-free. Alternative is that you could instead do something like STM and incorporate some notion of persistent race detection and failure atomic regions into the code. And maybe because of this, it may make it easier for the programmer to do things. But I don't know, like I think in our, yeah.
I don't think it's a valid program. Which one is right? I mean, they can both be right. This is the semantic issue. It's not really a program. It's not really an issue of how do you detect it. If two people are modifying the same thing, one of them should be doing it, the other one should not be doing it. I don't know how you should, there's no way for the computer to tell which.
I mean, you could do some monitoring, but the thing is that now, yeah, if given our software model, it is an incorrect program, but it's also requiring the programmer to expand what is and is not a correct program, right? And that's tricky. The main thing is to minimize the amount of extra thought they have to have, and maybe this is just adding one extra thing that just causes them to completely explode internally. So you don't want that. So yeah, I don't know. This is, I think, a big thing. I think in academia, like I presented this at PLDI and a similar thing, a lot of people were complaining that, oh, this model where potentially these undo logs could race, even if you wrote a properly data erase-free program, this is wrong. You have to do something instead. Although doing anything else instead isn't practical from a performance standpoint. So yeah, I don't know. It's something to still kind of think about. Another big thing is, as we were kind of talking about before, is with regards to lock-free algorithms, how do you do that in a persistent manner? Because all these hardware synchronizations are for visibility, not persistency. So, as I said, hopefully hardware will come out in the near future, or in the future at all. And that would be nice. But one nice thing, if you're using like a language, especially a managed language with NVM support, because the code's compiled dynamically all the time, what could happen is it would naturally kind of adapt to future hardware. As maybe right now it could use some type of software techniques for these atomic instructions or primitives. And then as hardware becomes available, it will be actually able to utilize it. So these are things that are kind of some issues with a general reachability. Because you're doing this transitive closure, a lot of things that maybe you don't want to become persistent is persistent, or even if it becomes persistent across a crash, you don't know exactly what you're supposed to do when you're recovering it. So an easy example is locks. If you're not persisting program state, you're just kind of like the execution state, you're just persisting the data. Across restarts, locks should just be cleared. But there's a lot of other different types of things that become persistent that may have behavior that's not always needs to be the same. So for instance, for like timers, file handler sockets, if a crash happens, really what do you want to do? I think probably the most reasonable default we have is just for them just to become null now and not to be closed. But in reality, the programmer will have to intervene in some way to say what the restart behavior for them is. And another tricky thing for Java is like threads, right? Because if a crash were to occur and a thread is being pointed to by some, it's reachable from this durable root. And what do you want this thread to do? Well, you could resume it at the point of its execution, but that would require persisting too much state. But let's say if it's this thread that's just doing some maintenance work, maybe you want to restart its execution to make sure it just kind of continues to maintain that data structure. But if it's doing like some type of one-shot action, then maybe you don't want it to actually restart again at the start of the application recovery time. But yeah, so there's this, in reality, I think for more complicated programs, there's going to have to be programmer input for these kind of different bimodal behaviors of what you want to happen in these different scenarios. So, yeah, I guess that's all I have for now. I'm running out of time, but right now, NVMs, it's difficult to program. We've introduced AutoPersist to try and make it easier to program. And I really believe that language integration is necessary, and it provides a lot more promise for both programmability and performance. But there's many problems that still need to be solved. And I guess, yeah, thank you for listening, and I'll take any more questions you have.